In this video, we're going to go through some VCE algorithmics old exam questions on the subject of recursion. Make sure you read the questions a bunch of times, pause them, try them, and then listen to my solution. Now, the first one, we haven't seen many of the styles of these kinds of questions where we have to do something that's quite unrealistic in an algorithmic computer science context. But we'll be prepared for anything, so we'll just go with it. And it's always good to think, like, what would you actually do in the like in real life? So Wally goes to wash his clothes, and we know for recursive algorithms there's a base case. So at what point does the dividing into two smaller baskets stop? Well, that's going to stop when we've got one item of clothing left. So our base case is going to be something like basket contains one item. And when that happens, you just wash the clothes. If that's not the case, if we've got more than one item, then we are going to divide it into two different baskets, and then we're going to recursively apply the algorithm on those two. So if we imagine what this looks like, we have our basket of clothes, and what we're going to do is divide that down. So this is called by the algorithm. We divide that into two baskets. And then for each of these calls, we divide those into two baskets. So we're then going to divide into that basket and that basket. And then we'll divide it into that basket and that basket. And these are our base cases. So base cases are here. And then likewise over here, we divide into those two baskets, each of those into two baskets, and wash those items of clothing. So if you haven't already, make sure you try and write that. And now let's look at the VCAA response. There it is. And it's a bit weird, like when one of the lines is wash the single item of clothing, notice that this doesn't return anything. And one of the points I'll be making later is we've got to make sure our algorithms return stuff. Now, they also have been a bit casual about splitting the basket down. We might go into more detail and say, well, if there's an odd number, we can work out like n plus 1 over 2 or something like that to find the number of items, whatever. Now, the next algorithm, again, with all of these, read the questions a bunch of times. Note this is not recursive. And again, think about what we're going to be doing. We're going to be taking a sock and comparing it to each of the other socks in the basket. And notice it tells us there are unique pairs. So straight away, hopefully you can see why there is something unneeded in my first algorithm here. These are two different algorithms which essentially do the same thing. So we run through and for each sock, each potential sock, each candidate sock in the sock list, we see if it's the matching one that we're after, and if it is, we return that pair. So we have to return two things here. That line return nothing, technically not needed because we know that every sock is in a matching pair. So we know that the first three lines will return something. Looking at the second algorithm, again, I think we've done a recursive one here, which wasn't necessary, but you might be in that mood. The recursive case, the base case shouldn't be necessary, but it would be remiss not to put it in there. And again, we've checked to see if the first item in the sock list is the one we're after. If it's not, we remove it, and then we run the find match algorithm again on the remaining socks. Hopefully you got something like that. And finally, we're writing a big algorithm to kind of bring all this together. Now make sure we're reading this carefully. What we need, so socks as the input and all pairs of matching socks. And we're probably going to be using the helper functions. Well, we are going to be using the helper functions. Tail recursive means the last line of our algorithm needs to be a call to itself. So really that's just a matter of getting the ordering right. There's not usually anything too hard about that. Have a go, and we will talk through this result. So we're saying we've got to call this with an empty list, like you might call this a default parameter in Python, but we don't do that sort of thing in Algo. So we're calling it with an empty list. And if there are no socks left in the list of socks left to sort, then we're going to return the pairs that we've got. That's only going to be relevant on one of the future recursive calls. So we take the first sock, so let A be the first sock. We could pick a random sock, doesn't really matter. We find a pair. We sort of implicitly defined our own abstract data type there. Pair AB is the result, that tuple of finding a match between the sock we chose and from the rest of the socks. We need to make sure we add that to pairs, the list of pairs. We need to remove the pair of socks that we just found, and then we return what's going to be the list of socks with the two that we just found, and pairs now has the two socks that we found. So each time we do this recursive call, list of socks goes down by 2 socks, and pairs goes up by 2 socks. And so we would need that recursive call, in fact, because we would need the base case, because once we get to the point where the list of socks is empty, then that means all the socks have been put into the list called pairs, and we have done our job. We've returned all the pairs of matching socks. Okay, next one. For whatever reason, I can't remember now, I've missed off the first 2 questions. Make sure you've read this, have a good look. Now, for part C, this is not relevant to recursion, but yeah, it's there. It'd be remiss of us not to mention it. I'm pretty sure this was the definitive answer. We actually, in terms of checking for safety, we could do this with a stack if we had to, but certainly for flipping the pile upside down, we would want access to all of the items. So we want to be able to access any item by index, not just the one on the top of the stack. Hard to see exactly how you'd get the 3 marks there, making sure 1 mark for saying that the top element is the only one that can be accessed, next mark for saying that that wouldn't be enough because we need to access all of them, perhaps, and then suggesting a new ADT and guarantee we get the mark would say why is that new ADT best. Okay, and we're going to write a recursive algorithm, check safe, to see if the pile is safe using the ADT that we've identified. Now the way, again, it's always good to think, what would I do in reality with these things? So take an example. Let's say I was doing this one here. The recursive algorithm is going to look at the top box and see if it's smaller than the next box. Okay. Now, if it is, then we can get rid of the top box. And now we can just work on the rest of the stack and say, now, is the second box, which is now the top box, smaller than the next box? If it is, we get rid of that one. We recurse on the next stack and so on until we get to our base case, which is where there is just 1 box. So if we get to the point where we've just got 1 box left, we can say, yes, the stack is safe, because a stack with just 1 box would definitely be safe. So that fits both considerations. If we were doing the one on the right, we look at 6, and we'd say, is 6 bigger than 3? No, it's not. So at that point, we return false. So essentially, we're going to keep going through, reducing the stack of boxes that we have to check. If at any point it becomes unsafe, we say false. And if it makes it all the way to the bottom, then we say it's true. Let's look at the pseudocode for that. We've specified our bits at the start. So remember, with every algorithm, a useful guide is to consider A, initialization, B, doing, and C, returning. So we've got to make sure we have all those elements, plus whatever else we want with recursion. So if it's a recursive call, a recursive algorithm, we need to have the recursive call, and we need to have our base case. So let's see, does this work? We tend to start with our base case, even though it's often what I would think of last. If the length of boxes is less than 2, or if the length of boxes equals 1, then we know it must be safe. So that is these lines here. That is our base case. And then we're saying if the first box is bigger than the second box, I feel like that is wrong. I think that needs to be smaller, doesn't it? So, well, it depends which way we've set them. So this is freeing, I haven't read it properly, have I? Look, boxes 0 being the bottom of the stack. So in fact, yes, we need boxes at the bottom to be bigger than the next one up. So we've gone this way. We've started at the bottom and checked the next one. Then we're discarding that, checking that one against this one, discarding that, checking 6 against 5, and so on. Absolutely fine. In both cases, the greater than or less than relationship is transitive. So if 13 is less than 10 and 10 is less than 6, we know 13 is, I meant to say greater than, who cares, greater than 6. So we've said if it's safe, then and again, we've been a bit casual with the pseudocode there, but for something this simple, for algorithmic students, we can take it that, that's a kind of a gimme in golf, right? It's accepted that we could probably have done that if we wanted to. If it's not, then we return false. Okay, last one. This question is one I have made up, and it's kind of how calculators might solve something. So if we're trying to solve an equation, x squared equals 2, you may remember on the older calculators you'd have to specify like a lower and upper bound. So we're going to have a solver which takes the target of 2, and we're going to say the solution lies between, let's say, 0 and 3. Okay, so what would we do to try and find the solution to x squared equals 2? And we'll say the positive solution, so well, the one that lies between 0 and 3. We would do 0 plus 3 divided by 2, which is 1.5. And we would do 1.5 squared is 2.25, which is too big. So now we're going to run solver. The target is the same, 2. The lower is still 0. The upper is 1.5. So we're looking between 0 and 1.5. We're going to do 0 plus 1.5 divided by 2 is 0.75, and then 0.75 squared is 0.5625. There's my pen bar, there it is. 0.5625, too small. So we're going to run solver again. Because it was too small, we're going to bring up that lower bound. So now we know it's somewhere between 0.75 and 1.5. And we're going to keep going. At what point do we stop? So we're going to stop when either these two numbers are really close together, like the upper and lower bound are within 2 decimal places, or we're going to stop when it's like the distance between like 1.5. So sorry, when you square it, the answer is close to the target, although that's not quite accurate. So we're better off doing the bound between lower and upper boundaries. So I've gone through like a concrete example of this. Obviously, it's not always going to be squared. It's just whatever. And now let's look at the example, see how that works. So there's the base case I mentioned. Going to 0.001 is probably slightly overkill, but we don't need to worry about the maths there. Whether it was upper or lower, we could return either. So we've said that we haven't got an accurate thing yet. I notice I put target at the end, but it doesn't make any difference. We find the halfway point between the lower and the upper and put that into secret. And if that is too big, then we return the lower and the midpoint. We run the algorithm again with that. And if it's too small, we go from the midpoint to the upper boundary with the same target. Okay, hopefully that's helpful. You can see some recursive algorithms, making sure when it's recursion, we always include our base case and we return the recursive call, something I didn't mention before. Sometimes people will leave out the word return and they'll just kind of run solver. And well, then that's not passing the solution back up through the recursive chain. So make sure we have something that passes it back up. And then in algorithms in general, we have our initialization, we have our doing phase, and we have our returning phase.